It's muted. I apologize. I don't know why. I thought anyway, probably I didn't. All right. So the only thing for those who are on Zoom, there are a few on Zoom, I wanted to say, I will repeat that when I come on Wednesday, so there is not much that you missed about the grades that I have put on Canvas. It's just that I have to correct a few grades that I added manually from the Top Hat exercises. The rest I will repeat on Wednesday, so I don't have to repeat it right now. The only other thing that I said is that we are going to have an exercise today, and then it's going to do on Wednesday in the morning. And so I will always put this information in the module, but also check your account. And if you see an exercise open and you have not done it, do it. All right. A lot of times I say that I will, like, for example, what was it? We had a quiz or something, an exercise, and I had left it on for quite some time. The reason I do that is, yes, I like to be fair to everybody and people who work to meet the deadline. I'm not that anxious to turn it off. I just want to make sure that people do it. This is the most important thing. So if you click, like after the lecture or the next day, and then you see an exercise open, even if it's one you thought you missed, if it's open, you should do it. So we're going to have an exercise today. That's the one thing you need to remember. Okay, from now, I would like to start with the lecture, which also you have in your notes. And it is Introduction to Transmission Line. One thing, unfortunately, I have not been able to locate my book. So the one I'm working on is an older version, and I don't have, do you guys have a book here? Do you have a copy, a paper copy of a book that I can borrow? No. All right. The one that I had is gone. So I don't know where I left it, but I cannot find it. It's not at home. It's not in my office. It's not in my bag. I will check again, the lost and found. The problem with this is that I cannot tell you exactly the sections. So I need to find a version of the most recent copy of the book. I'll check with the department to tell you the sections we're doing, but I will describe the sections to you. So we covered the front part. If you go and look at Maxwell's equations, in the chapter that says Maxwell's equations, it's chapter, the chapter is the same in title, but it changes its number. All right, this is yet another version of the book. And in this one, Maxwell's equations is chapter 9. Okay, let's see. Now, chapter 9 and 10 in this. Let me see what it is. Okay, so you go to chapter 10. This one. Okay, and then it talks about electromagnetic wave propagation. Look at the chapter after Maxwell's equations, that in the next chapter is on electromagnetic wave propagation. We've covered when it says waves in general, we covered 10.1, 10.2 practice. Okay, so these are the two that we have covered so far. And then we stop there, and from there, we are going to chapter that is called transmission lines. All right? And that's where we are here today. So I just need to remind you a few things. Where we left it last time was that now we know that if we use an AC source that creates a wave, so if our voltage, for example, in a circuit is a function of time, and in fact, also another to remind you, when we write a voltage or a current that is a function of time, we write it with a lowercase, all right? And we said that this will probably have a an amplitude, and it's going to be a cosine wave of omega t. Okay? So this is where a time function, where omega now is the radial frequency. Okay? And is equal to 2 pi f. And the units for the radial frequency is rads per second. The units for f are 1/second. Okay? And 1/second is hertz. So omega is in rads per second in units, and f is in hertz. Okay, V naught is volts, obviously. So I will write here the units in volts. Now, when you have a source like this, okay, it's a voltage source. Let's put it here. We said last time, and let's assume that you feed with this. You want to feed a load and assume this load is resistive. Now, what will it be a resistive load? I will show it like that. Resistive loads, now from this point on, I will show a load, any load, and I will explain what we mean by load. I will show it like this. All right, and why do I show it like this? Because ZL, which is the load, can be either resistive, a resistor, can be either a capacitor, can be an inductor, or can be any combination. And what is this load? So this is my source. The load can be a termination of my circuit, all right? And my circuit may terminate in an antenna. If the load is an antenna, and what we say the antenna operates around its resonance, all right? So the load, for example, I'm writing this because I'm using the appropriate terminology here. It's a terminology you're gonna hear me repeating. So load can be resistive, A, resistive, which means the Z sub L is gonna be R sub L, that's how I'm gonna indicate it. And what is a real implementation of a resistive load? It can be, so i.e. I will put here, could be an antenna at resonance, why do I say that? The antenna normally is a geometry that provides, like any geometry. If you are given with a generic load, assuming that the load is going to have everything in there, a resistor, an inductor, and a capacitor. So if somebody says a load, you assume the most generic case. If I want to specify it and say it's resistive, or I say an antenna at resonance, it means the antenna, which in general will have an R and a C, or an R and an L, or it's going to be resistive and capacitive, or a resistive and inductive. At resonance, these capacitance and inductance cancel each other. All right, it's the place where there is an LC kind of combination. So it gives you only the resistive part. And at resonance, this resistance is not ohmic. It's called the radiation resistance. Practically, it's everything that leaves the antenna and is propagating, all right? So an antenna will have can be a resistance, but you don't lose it into heat. Like ohmic losses become heat. An antenna will radiate. So usually an antenna at resonance gives you the radiation resistance which is exactly what you want to have for an antenna. And usually you show it by R sub L. Now, if the antenna, like any other real material, antennas are made of all kinds of different things, but mostly conductors. If an antenna is having, of course, its radiation resistance operates well, it's going to have a small amount of ohmic, all right? Every conductor has losses, everyone, with the exception of the ideal conductors. However, the ohmic loss is so small compared to the radiation loss, we never talk about it, all right? Now, the other possibility, so one case can be an antenna. The other can be a matching network, as we call it, matching network. You will see what is a matching network in this class. What a matching network does is that if I have two parts of my circuit, but they have the one has been designed for a load, because you always have to know your load before you design your circuit. You have to know where you're gonna be connected to, all right? And if you have designed your circuit to connect to 50 ohms, for example, and you have to connect it, for example, your circuit could be a filter. If you design a filter to have a load of 50 ohms, and instead, the next, whatever comes, the low noise amplifier, for example, that may come after the filter, does not have 50 ohms, but it has 26 ohms or 150 ohms, or it may have both a resistive and a capacitive, or a resistive and an inductive, all right, part. If it has a complex load, as we call it, complex, then you will have to put a matching network in between. So it takes the low noise amplifier that has a complex input load, presented complex load, and translate that into 50 ohms to be able, therefore, for all of the real power from your input, from your source, or from your other circuit to go through the matching network, all of the real power, and then be delivered to the load. The only idea, therefore, in circuit design is whatever real power you deliver from your source to be able to take it and give it to the load. If you do that, then you have done good circuit design. Of course, there are other constraints, all right? But the most fundamental from the electrical point of view is not to lose your real power. So it could be another matching network, all right? Which is gonna be in between two pieces. It could be a filter. It could be a low noise amplifier. We're not gonna do those in this class. Or it could be an oscillator. All right, so for us to simplify all of this, we are gonna represent each one of those with a Z sub L. And let's assume now that I'm designing a circuit for this one, for an iPhone. Let's assume that I design is part of a receiver, all right? So my antenna is somewhere here, outside. My circuit is inside. And I want now, and my source is inside, okay? So my source is somewhere here. And my source takes DC and makes it AC. All right, so there is a transformer from DC to AC. And then it delivers this AC that may be around frequency of 5 gigahertz. So it has an oscillator. So it takes the DC, uses the DC to excite an oscillator. The oscillator oscillates and creates 5 gigahertz AC. All right, and with some kind of efficiency. It's not 100%. So for example, if you use 1 milliwatt from your DC, it's not gonna turn that into 1 milliwatt for AC, it's much less. So usually those, like an oscillator or a power amplifier and an oscillator together create high frequency power. or an oscillator can be alone, but the power amplifier cannot be alone. It needs to have an oscillator next to it, all right? Because it says the word, it amplifies something. So this something has to be there. Neither one of the two has 100% efficiency. Neither one of the two takes DC and uses all of this DC power and makes it AC. They are about 60%, 70%. So they take, if they take 1 milliwatt of DC from your battery, they will change it into 0.65 milliwatts of RF. All right, so we're losing, you're losing that's it. I mean, technology has not been to 100%. I don't know wherever anybody's gonna do 100% transition. That will be a game changer, as they say. But anyways, that's where we are. And then from the oscillator, you have to go to the antenna. The oscillator cannot, if you put the oscillator directly to the antenna, a lot of bad things will happen, all right? Because the oscillator has not been designed to connect to this particular antenna. So you have to go through a number of other circuits in between. Okay, and then in addition to that, your oscillator is one place, physical space. Your antenna is at the outside. Your oscillator is inside your circuit. The antenna is on the cover of the whole thing. Otherwise, how is it going to radiate if you put it inside, all right? Not going to radiate. So to transfer your power from your oscillator to the antenna, you need to have a way to transfer it effectively. If you think about it, if I have an oscillator who converts only say 55 or 60% of DC into RF, and then I have to take this RF and then move it to the antenna after I do a number of things, then I need to make sure that I don't lose almost anything in the process. Because if I keep losing every time I go, I will go to the antenna and I will have like 1 microwatt, all right, to radiate, which does not make sense. So when we are to go from the source to the load, we need to confine whenever we just transfer, physically speaking, from one point in space to another, we need to confine the power. And we confine the power in the way of sending it there using the transmission lines. All right, that's what the transmission line is. Like I told you, if I have, for example, there are other applications which are not this small. You may have, like in a telescope. Telescopes, what do they do? Telescopes, there are telescopes, well, mostly the deep space telescopes do not send anything. When are you going to send something? There is no way you can send, because by the time it goes to the planet, which is 100, how do we call that? 100 light years, right? Thank you. Even there's nothing this close, but it's 100 light years, and the time it comes back, you're going to be dead. You're not going to be able to have enough time, to even see the second. So what they do, they only receive. And they take the signal, which is extremely weak already, extremely weak. And they try to remove the noise to process it. And then they try to amplify it, all right? Before it comes down where we read it and we see it and process it, of course, to read it and see it. Okay. To get this very, very small signal, until it comes out to me where I'm the scientist and I have to read it. It goes through a lot of circuitry. And then also, nothing is one on top of the other, all right? They are separated. Usually, you have seen telescopes, how they are. They're huge structures. I mean, the input to the signal may be 10 meters away from the closest low noise amplifier that you have. And it's very high frequency. You know why they're very high frequencies? Because the frequencies are determined by the chemical reactions on the surface of the planets, or the chemical reactions to whatever is happening they're looking for. So if there is a chemical reaction, usually there is a frequency that is radiated out of this. All right, there are particles that are produced, that they oscillate in particular frequency, and they pick those frequencies. And that's how they know that the so-and-so reaction is happening on this and this planet. All right, so these are very high frequencies, like in the terahertz. Terahertz means 10 to the 12 hertz. So what then, you have to have lines to take this signal that you have already tried to amplify, and then to take it to the place where you're going to process it. And you have to make sure that every bitty part of the signal remains, all right? So the design of these lines has to be very, very good. The lines have to make sure that they do not have any loss, or they have the least possible loss, all right? So when you design, therefore, to do that, that's where we're coming. So you need B, transmission lines to move the signal. 2, transfer the signal from one point to another. Okay, from A to B, say, A to B. And in fact, the way we are going to show those here, and I will explain why, from A to B. Okay. Now, let's go back to things that we have seen already and we feel comfortable with. What have we seen? That if we want to constrain, not allow to distribute rather, but to constrain well, physically rather, electric or magnetic energy, rather meaning to keep them in one space and to be able to control it, so you don't allow it to disperse physically, we need to have two conductors. You remember that? For electric energy, we need to have two planar conductors. We have seen, they don't need to be planar, but we have seen the two conductors that are planar, like a capacitor, if they're very, very close together, and that distance is much less than their size, the one, say, side of the conductor or the total area. Let's assume that the total area is X, Y, and Z. It has to be the distance much smaller than any size that characterizes the shape of the conductor. If that happens, for example, two or three microns for integrated circuit, 2 or 3 microns distance between the metals, and the metals can be 100 microns square, all right, this kind of range. Then you are very successful in storing all of the electric energy in one particular space, all right? And if you can then use that kind of structure to move it, then you contain most of it, or almost 100% of it, all right? Now, with magnetic fields, we also found something similar. We looked at wires, but if you take the same two conductors and use those to move the current through, all right? Because a structure like that is going to have both a voltage, there's going to be a voltage that are created by this source plus a current that is going to flow. The current that is going to flow here. So in circuits like that, when you put a voltage source, you create a current too. You have seen that from circuits, all right? I mean, this is not a new thing. We know that, both in statics and in AC, in analog. All right. So if now you have this current to flow in the same two kind of conductors, you also constrain in that same physical space your magnetic energy. All right. So practically, what I would need to do in a situation where I have an AC source, and when I have an AC source, remember what I said, we create both electric and magnetic fields. So practically, the AC source is going to have, of course, it creates a voltage that applies, and therefore the voltage is responsible for an electric field and creates a current. Both voltage and current are functions of time, and the current creates the magnetic field. But the voltage and the current are not independent, they are related. All right, in a circuit like that, you know your RLC circuits. If you have a known R, a known L, and a known C arranged in some kind of configuration, and you have a voltage, will you not able to find the current? The current is not independent. It depends on the voltage and it depends on the kind of circuit you have. The same thing applies here. All right, so your current and the voltage are connected, which means that the electric and magnetic fields will be connected, related. That's why we call it electromagnetic, which means then both of them you can, in an arrangement like this, where you have a voltage that creates a current, and then both the voltage and the current will be related, and both of them will be functions of time, and both of them will oscillate like we saw last time. Then the voltage will apply here, and the current will go around and come back. All right, that's how it is. Because the current, when it goes like this on one part of the circuit, and then you have these two conductors as we've seen before. Let me now place them here. All right, we have seen that if I were to put here the following two things. Think now, this is a combination of symbolic and physical representation. Assume that you had here a very long conductor, like a plate like this, which is kind of narrow along this direction. Let's call that W. And which is kind of long along this direction. Let's call this L. And let's now put the other plate underneath it. Before I do that, let me also use this color for the upper plane. You put the lower plane underneath it, and then I have, it's identical. So practically now it's like I have something similar to the capacitors that we've seen, the parallel plate capacitors. They are not square, they are kind narrow and long, all right? They are two plates facing each other, and they are in a distance, but the distance is small. You remember we said that to be able to combine the electric energy, you have really to have the two plates in a very small distance compared to their width and their length. And so that's what we assume here. All right, and then if this is the thickness, the distance, vertical distance between the two conductors, I call that H. Here, the assumption in this case is that H will be much smaller than W, and H, of course, and W is going to be smaller than L. Can be much smaller or smaller than L, but not the same or bigger. Okay, so that implies that H is going to be much smaller than the length L. Now, if we do that, and I say, okay, what I have done so far is the following. I have a source, I have a load. And then I said, I have a distance, I need to move. The excitation, the power that this source generates, I need to find a way to move it to where my load is because they are physically separated. And I know that the distance between my source and my load is L. And let's assume that L, to also be realistic, all right? L can be 150 microns for integrated circuits, for ICs. Or L can be 2 or 3 meters for antennas and large systems, radars and so forth. All right. Telescopes, even bigger. L can be 10 to 20 meters in telescopes. Okay. So whatever the distance is, that length can vary. So definitely, of course, there is no problem in making sure that my distance between the two conductors is going to be much smaller than that. Here, it's of course, the smaller the length gets, that's where I start feeling the constraint. H has to be much smaller than L, and H has to be much smaller than W. If I choose this one as my length, let's assume that I do an IC design, then W, if therefore L is 150 microns, then W, I will make it to be about 2 or 3 microns. And then H, I will make it to be half a micron. Where in this particular case, therefore, let me do one more. My transmission line will look like this. I will have, of course, to use a substrate to place it. So I'm going to have a different color for substrate. I'm going to have a substrate here. Make sure that it looks nice. Okay, the substrate is going to be half a micron. Well, I can, yeah, all right. And then on top of this, I will put one metal. And in fact, all right, let me do it in two separate. One is going to be a side view and the other is going to be a top view because I cannot do it in 3D and do it carefully. So one is going to be one metal here. And then the other is going to be another metal here. All right, so let's assume that we have this one on top and this one below. And here is going to be silicon oxide, for example, a low epsilon material. So let's assume that this one is silicon oxide. And this one is the thickness between the two conductors. And now let's look on the top. On the top, I'm going to have the substrate, whatever, here. And I'm going to have the one conductor is going to look like this. On top, and the other is going to be underneath it. So practically, if I were now to do it here, then the conductor will look like this. All right, so here it will be the conductor. On the top conductor, and the lower one is going to be like this. All right, and then in between these two is going to be the material, the dielectric. And I'm going to connect to the left of this my source, V, and to the right of this, let me in fact remove this for a moment. Now I don't need it very much. I'll put that here. And to the right of this, I'm going to put my load. Let me do it differently. Okay. All right, that's the load, Isabel. and this is L. By choosing these dimensions that you have seen above, this is to be W, for example, this is W. And W is 2 to 3 microns. H is 0.5 microns. I can make it even smaller because the smaller it gets, the more confined. I can do it 0.2 microns. I can develop a 0.2 micron silicon oxide. And that's H. And this is the length, L. And the length can be 150 microns. All right. And let's assume that my source here is V naught cosine omega t, where F, all right, which is omega is 2 pi F. F here, let's assume, is 23 gigahertz. And how much is, or 20 rather, so we don't need a computer. How much is free space wavelength? You need to remember, free space wavelength. You remember what wavelength is? If cosine omega t is something like that, wavelength is this. Okay? So the wavelength for 1 gigahertz is 30 centimeters. 30 centimeters in 1 gigahertz. It is therefore 3 centimeters, so you remember how to do it, in 10. And how much is going to be in 20? 1.5 centimeters. Okay, so lambda is going to be 1.5 centimeters in 20. Now, 150 microns from 1.5 centimeters is very small. So practically you can assume that your load is next to your source, all right? So in terms, there are not too many. If you think that this is 150, 1.5 centimeters. And if I were to place my source here, if my source were here, my load would have been very close to it. I cannot even show you how close it would be. However, if my frequency is 200 gigahertz, all right, which is in fact one of the frequencies they're using for autonomous guiding, autonomous vehicles, all right? So in that case, it will be 0.15 centimeters. So in that case, my lambda would have been 0.15 centimeters. And if I'm going to terahertz frequencies, because people can use terahertz frequencies for short range communication. So, and if therefore, F is 2 terahertz, which makes it 10 times higher than 200 gigahertz, then lambda will be 0.015 centimeters, which makes it 0.15 millimeters, which makes it 150 microns. See what happens? So a given length for different frequencies, it may have much more of the wave in there. So my load would have been here for 2 terahertz. My load would have been in the middle for 1 terahertz and so forth. And it would have been extremely close to the source for much lower frequencies. So the physical, every time you do a design, and you will see that we will always translate, there's no point of saying, why did I do this exercise? Because if I have this kind of problem, if I want to design this transmission line so it connects my source to the load in a way that I do not lose power, and we will talk about that, what I mean. But the bottom line is whatever generates here to go there. All right, that's about it. To be able to do that, there is no point of keeping my length in physical units. It means different things given my source. It would always be important to keep my length in fractions of wavelength. So I will always give you this length, not in physical dimensions, in all design, but in fractions of wavelength. What is it? Is it 0.1 wavelength? Is it half a wavelength? Is it a quarter of a wavelength? And you will see that in all of the transmission lines, we're going to talk about lengths in wavelengths. Because then, if you do your design in wavelengths, then what will you be able to do successfully? To go and apply to different frequencies. If I do my design in physical lengths, every time I will have to do a similar design for every other frequency. All right? So this is what I wanted to cover so far. And then taking this line that we used as an example, which in fact is called a parallel plate transmission line. There are different derivatives of this line. When the ground, if you call this the ground, becomes bigger than the top, conductor is called microstrip. All right. When they look like that, they call strip line. It's called like a parallel plate waveguide or strip line. If the ground comes to the same surface with a line, it's called coupled strip line. I mean, if the ground moves to different locations, but they're very close to each other, right? We are not going to look at those. The book has different, we'll talk about this next time, I don't want to get that, but this one is called a strip line. It's a very popular line that people were doing some time ago. Or parallel plate waveguide. Okay, and we use it. We are going to start with this, and then eventually we're going to go into a symbolic form. You will see that next time. But I wanted to tell you why we are using these transmission lines. All right, we're using to transfer power from one point to another, and why all of our